Hi everyone. Here's the next lecture. Sorry, I've been sick and haven't been able to be in class, but at least this gives you a chance to see this material while you're still in your pajamas. Okay, so we'll get started here. Announcements. Just wanted to remind you to register on Connect. Okay, I've gotten some emails from some of you saying that you've had some difficulties. I'm looking into that. But if you're still having difficulties, if you haven't been able to register, you can go ahead and contact McGraw-Hill support. I included the URL for how to get in touch with them in the email. It's the last link in that email. So if you still haven't been able to get connected to the course, you should get in contact with them, or ask friends. One other possibility is if you had some difficulty, you might try registering with a different browser. I've heard from a couple of people that they tried with Chrome and it didn't work, but then they tried with Internet Explorer and it did. Okay, so you could just try a couple of different things there to see if you can get it to work. Once you're in, hopefully we won't have any more difficulties. Okay. Now this is going to be important because we're going to be starting to do Learn Smart activities and homework activities. Okay. Learn Smart activity number 1 is going to cover this lecture, and it's available now on Connect. Okay. Because people are having difficulties with registering for the course, I'm not making it due right away. It'll actually be due next week sometime. Okay. So I'm not totally sure when that's going to be, but plan on having that done, say, by the end of the weekend. Or if you're having trouble getting registered, you can contact me. I don't have a problem giving an extension if you've had trouble and you haven't been able to register. But I don't want everybody to fall behind just because a couple people are still having trouble getting on Connect. All right. So what are we going to talk about today? So last time we talked about organic molecules, and today we're going to start talking about Chapter 12, which relates to phases and phase changes. Okay. So we're going to look at section 12.1. So if you're following along in the book, this is where you want to be looking. Section 12.1. So we're going to do an overview of phases and phase changes. And then in 12.2, we're going to look at heating and cooling, phase changes, phase equilibrium, and phase diagrams. Okay, so here we're dealing with a lot of physical attributes of chemical substances. Temperature, phase changes. Okay. All right, so why don't we go ahead and get started? Phases of matter. So I just used the word phase an awful lot, and for some of you maybe that makes sense. For others it doesn't. So let's talk about what a phase is. So in a lot of ways, it's maybe not exactly true, but in a lot of ways we can say that the word phase is synonymous with the word state. Okay, so we've been talking about states of matter. Okay, so a state, a single contiguous chunk of matter that's all in one physical state is a phase. So you can think of phase as being synonymous with state. Just to review, this is something that you probably learned in elementary school or middle school, but the common states of matter are solid, liquids, and gases. Okay. And we know from all the things that we've studied before that matter consists of particles, either atoms or molecules, right? And those particles, so now we're thinking about the particles that make up a particular state of matter or a particular phase, okay? And if you remember from the beginning of Chem 111, things have two different kinds of energies, okay? We've got kinetic energy, which comes from the motion of something. Now we're talking about particles, so we're thinking about particle motion. And so particles have kinetic energy, and that kinetic energy comes from the fact that the particles are moving. Now, one thing that I don't remember if we really talked about too much before, but one of the key things here is that the average particle kinetic energy in a substance is proportional to its temperature. Okay, so the higher the temperature, the larger the kinetic energy of the particles that are in a substance. Okay, so temperature essentially is a measure of the average particle kinetic energy of whatever it is that you're measuring. Okay, So we've got kinetic energy coming from the velocity, and that kinetic energy actually causes particles to disperse. The fact that they're all moving means that, and the fact that their directions, the directions of the particles, are essentially random. They come from, the directions are essentially determined by the collisions that the particles encounter. That causes the particles to disperse. Okay, so they're not likely to all come together. Rather, they're more likely to move apart from one another, to fly apart. Okay, so that's due to kinetic energy. Now the other type of energy is potential energy, and that comes from the relative positions of particles, from the interactions that particles have with one another as a consequence of their positions relative to one another. Okay, so the potential energy comes from the attractive forces between particles. And since those forces are attractive, potential energy actually causes particles to gather together. Okay, so we've got kinetic energy on the one hand, which causes particles to disperse, to fly apart. And we've got potential energy, which is causing particles to gather together. Okay, so let's talk a little bit about attractive forces. There's essentially two general classes of attractive forces that we're going to talk about here. Okay. The first one is what we can call intramolecular forces. So you might not be familiar with this prefix intra. Okay. That's not the same as inter. Intra means inside. So intramolecular forces are forces that are occurring inside of molecules. And what intramolecular forces do is they hold atoms together to form those molecules. Okay, so these are the forces inside molecules that are holding the atoms together in order that the molecules don't spontaneously fly apart. Intramolecular forces, like we said, they're the things that determine what the molecule is. So as a consequence, they determine its chemical identity. What the atoms are that are being held together in this structure, and the structure itself, the molecule itself, that determines the chemical identity. Okay. All right, so that's intramolecular forces. The next one is intermolecular forces, and inter means between. Okay, so intra means inside, inter means between. And these are the forces, like the name suggests, that are between molecules. So these cause molecules to attract one another. And sorry about that. These cause molecules to attract one another, and they determine what phase a substance is going to be in. Okay, so how strong the intermolecular forces are, along with what the temperature and the pressure that the substance is experiencing, those things are going to determine the physical identity of the substance. Is it a solid? Is it a liquid? Is it a gas? Those are the things that are determined by the strength of the intermolecular forces and the temperature and the pressure that the substance is under. Okay. Okay, so we're thinking now about the different phases that a substance can be in. So let's talk about the different possibilities and the characteristics of those phases. So one phase, probably the simplest one, is a gas. Okay, so this is something that we have all around us all the time, something that we're sort of familiar with, but maybe we don't think about it too carefully or too much. So let's talk about the specific characteristics of gases. The first one, and probably the most important one, is the fact that gases have a very low density. As an example, gases, so water, here as our example, has 0.03 moles per liter when it's under a pressure of 1 atmosphere and at 100 degrees C. So that's only 3/100ths of a mole per liter. So that's a very low density. Another thing about gases, and this is related to the low density, is because the density is really low, particles are far away from one another. And so the molecules in the gas don't interact very much. Because the particles or the molecules, or it could be atoms, you could have a gas of, say, neon or argon. Those are monatomic gases. The molecules don't interact very much, or the atoms don't interact very much. And the consequence of that is that there's very little potential energy between the particles. Okay, the particles are far apart. Because they're far apart, they don't interact very much. There's very little potential energy. Okay. Because the particles are far apart from one another and they don't really interact, there's not really any order. So if I have some information about the location of one atom or one molecule, I don't have no way of really accurately predicting where another molecule is going to be. Okay, and that's different from the situation with liquids and solids, as we'll see. In terms of some of the properties, the ways that gases behave, they expand to fill the container. Okay, we know this. They can flow easily. Okay, so it's very easy, for example, to pump things, or if I have if I were just to look at this Erlenmeyer flask here in the picture, and I pulled off the stopper, the gas would flow largely out of the container and into the atmosphere. So not only would it flow, but it would expand to fill what's now its new container, the atmosphere. Okay. Because the particles are far apart and they don't interact with one another, it's very easy to compress gases. Okay, this is different from liquids and solids, which are not easy to compress at all. Okay, so these are kind of the key properties of gases. Very low density, very little potential energy, no order, expands to fill the container, easily flows, and easily compressible. Okay, next one, liquids. Liquids, in contrast to gases, are really quite dense. So we said before that our water vapor at 100 degrees C and 1 atmosphere has a density of 0.03 moles per liter. In contrast, liquid water at 100 degrees C and 1 atmosphere, so the same conditions, liquid water, there's 53.24 moles per liter. So it's about 1,000 times more particles per liter than in the case of the gas. Because the particles are so close, because of this high density, the molecules interact a lot, and there's a lot of potential energy between the molecules. There's short-range order, and basically what that means is the particles are close to one another, and so if you know where one particle is, you expect to see another one close by. Okay, so that's kind of short-range order, or more specifically what you can say is, because the particles are close together, any one particle has some number of particles surrounding it. And so there's kind of like a shell of particles around any one other particle. So that's what's called short-range order. The volume that the liquid takes up is fixed. Okay, it doesn't expand to fill the container. But the shape is not fixed. Okay, so what that means is that it can flow. If I were to tilt the Erlenmeyer flask in this picture, the shape that the liquid takes, it would conform to the contours of the flask, but its overall volume would remain fixed. Okay, I just said that. All right, so, well, let me recap this. So, okay, so liquids, they're dense, a lot of potential energy because the molecules interact a lot because they're close together. Because they're close together, you got short range order, fixed volume, but the shape itself, the particles, it turns out, can move around one another. They're not fixed next to one another. Okay, their locations are not fixed. And so that allows them to flow past one another and around one another. That means that the shape winds up not being fixed and that the liquid can flow to conform to the contours of the container, but it doesn't expand to fill the container. Okay. All right, and then the last one that we're going to talk about is a solid. Solids are very dense. They're usually not an awful lot more dense than liquids. Okay, but yeah, they're usually only a little bit denser than liquids. In this case, the molecules of the three phases that we've looked at, the molecules in solids interact the most, and they actually interact so much that they are fixed in position with respect to one another. So you can see that here in the picture, that the particles are in an orderly pattern. Okay, they're in this sort of, yeah, they're in this nice pattern that repeats itself. And what that means is the fact that this thing repeats itself over and over, that pattern repeats itself, means that there's both short range. So if I were to pick an atom here, then it's got, I can predict that there are going to be these atoms around it. But then I can also say with a lot of certainty that further away, I'm going to know where a particular atom is because of the repeating nature of this pattern. So there's both short range and long range order. We know that the shape and the volume are fixed. This is an important property of solids. It's something that makes solids useful to us in building things. So those are the most important properties of solids. Let's move on here. So phases of matter. You might be wondering at this point what it is that dictates what phase something is going to be in. Okay, so we sort of know already that, for example, at high temperature, water is a gas. At intermediate temperatures, it's a liquid, and very low temperatures, it's a solid. Okay, and so what that essentially is telling us is that the phase of water, the phase in which water exists, depends upon the kinetic energy of the water molecules. Okay, we said before that temperature is a measure of kinetic energy. And when you're dealing with a specific type of molecule, the strength of its potential energy, the interactions between the particles, are essentially fixed. Okay, that's a property of the molecule, how strongly it interacts with other molecules. And so the only thing that we really have control over is how much kinetic energy the molecules have. Okay? And it turns out that the phase of the matter depends on this balance between kinetic and potential energy. So if I have high potential energy, and recall, potential energy causes particles to gather together. There's an attractive force that pulls them together. So if I have high potential energy and low kinetic energy, my substance is going to be a solid. Now on the flip side, if I were to sort of reverse the situation and I had high kinetic energy, meaning I'm at high temperature, and I don't have very much potential energy to hold the particles together, then I've got a gas. Okay, so high potential energy but low kinetic energy means a solid. If I've got high kinetic energy and low potential energy, then I've got a gas. And if I'm somewhere in between, then I might end up with a liquid. Okay, so if I've got kind of intermediate kinetic and intermediate potential energies, then I'm going to have a liquid. Now, as you know, matter can change phases. And what we're going to be doing now, essentially for the next couple of slides, is looking at what's involved in phase changes. And we know that as temperature increases, the particles are going to move faster. And if they're moving faster, they can actually overcome attractive forces. Okay, if they overcome the attractive forces, they're able to kind of break apart. Now, if I flip the direction of things, if I'm decreasing temperature, then the particles are going to move more slowly, right? And the attractive forces between the molecules or between the atoms are going to pull the particles together, and I'm going to have something that more like a liquid or a solid. Okay, so as T increases, particles move faster. I'm going to end up with something like a gas. As T decreases, particles are going to be pulling together, forming liquids and then ultimately solids. Okay, so let's talk about some terminology. We've got actually 6 different phase changes that we want to talk about. We've got the phase changes that can occur between solids and liquids. Okay, so these are some things that might be familiar to you. So the direction of the arrow here is really important. We're saying we're starting with a solid, going to a liquid, and we're going to call that melting, just like we do in everyday terminology. In chemistry, though, a lot of times people also call this fusion. Okay, so fusion, you'll see sometimes there are certain energies, enthalpies of fusion are listed, and they'll have, it'll be a H sub F, something like that. That F refers to fusion, which means melting. Okay, so you just so you're aware of that. If we have the opposite phase change, going from liquid to solid, that's going to be called freezing, obviously, in sort of everyday language. In chemistry, we'll also often call that solidification. All right, so those are the things between solid and liquid. If we've got a phase change between a liquid and a gas, these are also things that should be relatively familiar to us. Okay, so in the case of a liquid going to a gas, you can also think of this as a vapor, right? And so if the liquid turns into a gas, it's becoming vaporized, or we call that vaporization. Now, if we have a gas and that's changing into a liquid, just like in the summer when you've got a cold glass of water or something, you end up condensing water from the atmosphere onto the glass. So that's called condensation. And then this is going to be the one that's the least familiar to us. Okay, so we've got a gas and a solid involved. And you may not be aware of this, but you actually can have phase changes where the phase changes directly from a gas to a solid or from a solid to a gas without going through the liquid phase. Okay, and so if I have the phase change going from solid directly to gas, that's what's called sublimation. Okay, and people say that a substance sublimes when that occurs. Okay, so sublimation is simply the phase change when a solid turns into a gas. And the reverse change is called deposition. Okay, and what's happening here is you've got essentially a solid surface and you've got these gas molecules and they're coming down and depositing on the surface. And the solid is growing because these gas molecules are coming down and then sticking on the surface. Okay, so that's called deposition because we're depositing gas particles on the solid surface and the solid grows. Okay, so those are 2 things that you're going to have to memorize. You're going to have to know that sublimation means solid to gas and that deposition means gas to solid. Okay, so we've got phase changes covered now, I think, at least in terms of the terminology. Let's look at how energy, or more specifically enthalpy, is involved in these things. Okay, so what we haven't talked about so far is whether energy is absorbed or given off when these phase changes occur. Okay, we've actually got 2 types, just like the chemical reactions that we talked about in 111. So we said in 111 that there are 2 types of chemical reactions. There's exothermic and there's endothermic. Okay, and we said that exothermic reactions give off energy and endothermic reactions absorb energy. They take energy from their surroundings. So the same thing applies here. Changes where particles that are involved in the phase change, when they lose energy, which is to say that they give off energy, So if they lose it, someone else is gaining it. Particles lose energy. Those changes are exothermic. Energy is leaving the system that we're looking at, which in this case is the particles. Okay? Now the flip side of that, or the reverse of that, is changes where the particles gain energy. Now if the particles are gaining energy, then energy is flowing into the particles. If energy is flowing into the particles, then the change is endothermic. Now what we can say, one of the things that's confusing about this terminology is, for example, that in some cases exothermic reactions occur when we directly cool some number of particles, right? So if I put water in the freezer, I'm actually cooling the water. But the solidification that the water undergoes as a consequence of that is an exothermic process. Okay, so it's losing energy. It's essentially giving off heat. But it feels strange to say that because we're sort of taking the heat from it. It's not necessarily. It doesn't feel like it's spontaneously giving up the heat. In reality, it is. We put it in a freezer, which is colder than the water, and so the heat flows spontaneously from the water to the cold freezer, and as a consequence, the water freezes. Okay, but in any case, the bottom line is if the system that we're concerned about, which in this case is the particles, if it loses energy, then it's an exothermic reaction. If the stuff that we're concerned about, in this case the particles, gains energy, then it's getting energy from somewhere, which means that it's an endothermic process. Okay, so let's divide up all of the different phase changes that we named on the last slide and categorize them as endothermic or exothermic. Okay, so if we're dealing with a solid liquid phase change, let's look at how these things break down. Okay, so we said before that solidification requires energy to be pulled out of water, for example, so that's going to be an exothermic change. And the endothermic change is going to be melting. Okay, so melting is what happens when you take a solid and you add energy to it, then it melts. Okay, so the fact that we're adding energy to it and it's gaining energy makes it endothermic. The fact that freezing or solidification requires that we remove energy from the system, that makes it an exothermic reaction or an exothermic process. It's not a reaction. All right, so if we look at gas and liquid changes, well, spend a minute here and just think about this. Okay, the two things that we're looking at are boiling or vaporization, and then the other one is condensation. So vaporization and condensation, which one happens as a consequence of energy being removed, and which one happens as a consequence of energy being added? Okay, so hopefully you've got this kind of figured out. We can talk about it, but the basic idea is, probably as you figured out, from boiling, we know that if I'm going to boil something, I need to put a lot of energy into it. I put it on the stove, heat it up. Okay, so boiling or vaporization is our endothermic change. Okay, now it might not be totally obvious that condensation is the exothermic change. It obviously is, has to be. Right? But the reason that water condenses on the outside of your glass in the summer is that there is water vapor in the air and it's at room temperature, which might be pretty hot in the summer, right? And when water vapor molecules come in contact with a cold glass, they actually transfer their heat energy into the glass and then they stick. So essentially what's happening is energy is being transferred from the water vapor into the glass or into the contents of the glass. And so the water vapor is losing energy and it's condensing on the glass. Okay. So if you want to keep your drink cold, you want to prevent condensation because condensation is essentially transferring energy into your drink. Okay, so try to avoid condensation if you want to keep your drink cold. All right, last one. We've got gases and solids. So our two options here are deposition and sublimation, right? And so we have to figure out which of these things is going to be endothermic and which is going to be exothermic. So in general, what we can say is anything that results in a gas being formed probably requires energy to be added to the system, which means an endothermic process. Okay, so we said sublimation is the change when you go from solid to gas. Okay, and that produces gas. So sublimation is going to be our endothermic change. And obviously that leaves deposition as our exothermic change. But what we can say is essentially the same thing as we said just with condensation, that it's exothermic because what ends up happening is the gas deposits on the surface. It had been flying around at high speed, and then it ends up hitting the surface and it sticks. And it's going to be transferring some of its energy into the solid. Okay, and so as a consequence, it's actually losing energy. The particles that we're looking at are losing energy, which makes that an exothermic change. Okay, so hopefully that's fairly clear. Let's look at some examples here. Here's an example for water. Okay, so and this is putting actual numbers on it. What we're interested in doing here is to kind of look at the magnitudes of these things and to get a sense for how everything fits together. So if I've got the transition between liquid and solid, here it turns out that the energy involved in this is the enthalpy, standard enthalpy of fusion. It's 6.02 kilojoules per mole. Okay, make sure that you notice that K there. That makes a big difference. And if we were to apply Hess's law, we could basically figure out that the opposite process should have the same magnitude, but the enthalpy of that process should have the same magnitude, but a different sign. Okay, so what this tells us is that the enthalpy of freezing is just the negative of the enthalpy of fusion. Okay, all right, so solid to liquid, as it turns out, this is actually not a very large magnitude. And you'll see that here when we look at the difference between, or we'll look at the energy involved in a transition from liquid to gas. So the endothermic change is boiling, and it turns out that or vaporization, and it turns out that the enthalpy change involved in vaporization is 40.7 kilojoules per mole. Okay, so that's almost a factor of 7 larger than the enthalpy of fusion. And as we said before, the exothermic change is just the negative of the endothermic change. All right, and then finally we're going to look at transitions between gas and solid. And let's look at that. So here, the delta H of sublimation is 46.72 kilojoules per mole. So if I want to take a mole of a solid, in this case ice, and I want to turn it into gas, I have to add 46.72 kilojoules to that thing in order to turn it into a gas. Now you might be looking at this and you'd say, oh, well, this is interesting. So I've got 6.02 kilojoules for kilojoules per mole for the transition between solid and liquid. And I've got 40.7 kilojoules per mole for the transition between liquid and gas. And 46.72, this is just the sum of the two other ones. So I'm going, in this case, I'm going from solid to gas directly, and it turns out to be just the sum of the transitions between solid and liquid, and then liquid to gas. Okay, so this is another application of Hess's law, that I've got these transitions, these energies involved in these phase changes, And it doesn't matter whether I start with a solid, convert it to a liquid, and then convert the liquid to a gas, or if I start with a solid and convert the solid directly to a gas. Either way, the energy involved is the same. Okay? And then, of course, for deposition, which is the exothermic change, the enthalpy involved is just the negative of the enthalpy of sublimation. Okay, so just to recap the important points here, the relative magnitudes, a couple of things that you can look at. Relative magnitudes of the delta H of vaporization, okay, which is pretty large in comparison to the delta H of fusion. Okay, so that tells us that the difference in energies between gases and liquids is a lot larger than the difference between liquids and solids. We can also say that this thing, the delta H of sublimation, is just the sum of the other two, delta H of fusion and delta H of vaporization. Again, another application of Hess's law. And these things, the enthalpies of the endothermic and the exothermic change are the same in magnitude, but opposite in sign. Okay? We can see pictorially in this picture, we can see what we were just talking about before. Okay, so we've got this representation. We've got enthalpy over here. This is on the y-axis. The x-axis doesn't really mean anything, but we've got solid, we've got liquid, we've got gas. Okay, and what we can see is that the enthalpy change between solid and gas, this is the longest one. Okay, this is the largest change here. And you can also see that these arrows, the enthalpy change involved in melting, going from solid to liquid, and then the enthalpy change going from liquid to gas, they just add up to the enthalpy change of sublimation. Okay, and then you can see similarly that the length of the arrows on the for condensation and freezing and deposition, these arrows are the same in length as their counterpart on the other side, okay, but the direction is opposite, which means that the sign of the change is different. Okay. But in any case, when you start with a solid and you add energy or enthalpy, you go up and you end up creating a gas if you add enough. If you take energy out, you produce a liquid and then a solid. Okay. Okay, so let's take a quantitative look at phase changes. So far we've just kind of been talking in generalities, talking conceptually, right? But we're going to want to be able to do some sort of quantitative calculations. And so we need some way to actually relate the energies or the enthalpies involved in phase changes to heat and to temperature changes. Okay, so let's go back. This is going back to, I guess, chapter 6 in the book. Some good old material from Chem 111. Okay, so if you recall, we had this equation, Q equals mc delta T, and this is just the mass of the substance that you're heating times its specific heat capacity. Okay, that's what the small c means, specific heat capacity, times the change in temperature. And that gives us the amount of heat involved in that change. So whenever a substance is being heated or cooled, this is the equation that you want to use. Now, if I want to quantify how much heat is involved in a phase change, I need a different equation. Okay, and that equation is this. Okay, it uses the enthalpy change of the phase change, and N simply indicates the number of moles. Okay, so delta H is typically given in kilojoules per mole, and if I want to know how many kilojoules total I have, I need to know how many moles. So that's where N comes in. So we've got the heat involved in the phase change is just the moles of the substance changing phase times the delta H of that phase change. So this equation applies whenever the substance is actually changing phase. So now we've got essentially two equations that we can use whenever there are any changes happening. We've got an equation that we can use for temperature changes. That's this one up here. And then down here, this is the equation that we use whenever we have any phase changes. And both of these give us a way of calculating the amount of heat that's involved in the change. So you can imagine that there are going to be ways that we can use this to figure things out. But let's look first at kind of a graph. This is kind of a busy diagram, but it gives you a pretty interesting view of what's actually happening when, in this case, water goes through a large temperature change. Okay, so what's happening here is we're starting with water at 130 degrees C. Okay, and we're ending with ice at minus 40 degrees C. Okay, and what's happening as we do this is we're starting with a gas, right? So we've got a gas here. And what's happening is heat is being released. You can see that essentially what's happening is on the x-axis, we've got the amount of heat that has been pulled out of the gas or out of the water. Okay, so the further we go to the right, the more heat has been pulled out. So we start off at 130 degrees, and some heat is being pulled out, and so the temperature goes down. But throughout this region, all of the molecules are all in the gas phase. Okay, and that's what this thing at the top here is kind of showing us. This is showing us that we've got just gas. Okay, in this phase, now what happens is here we've just hit the boiling point of water. Okay, and as we remove heat, additional heat, now what's happening is we're not actually changing the temperature, but instead what we're doing is we're converting gas to liquid. Okay, so throughout this region here, we have both liquid and gas. So both of those things are present. Okay, so starting at this point, we start converting gas into liquid. Okay, and so over here at the very beginning, at the left side of this region, we've got mostly gas, and over here, when we're about to exit that region, we have almost exclusively liquid. Okay, so if you wanted to, you could draw some sort of line that would indicate how much gas and how much liquid you had. So you might say that, well, here I've got a well, I'm not going to do that, but in any case, we've got it's like at the very beginning it's all gas, and at the very end of this region it's all liquid. Okay, and so again, it's the important thing to note is that in this region we're not changing the temperature. Okay, the temperature does not change. What does change is the relative amounts of the gas in the liquid. As heat is leaving, gas gets converted to liquid. So at the beginning of that region, it's all gas over here, right? And as we remove heat, we're transferring or we're transforming gas into liquid, and that happens continuously until we get to this point, at which point we've converted all of the gas into liquid, and now we just have liquid. So now once we just have liquid, right, which is shown up here, now there's no more phase change. The phase change is done. Now what we've got is just a temperature change. Okay, and so as heat is drawn out, the temperature of the liquid goes down along this line. Okay, and then we reach the freezing point. Okay, that's 0 degrees C. So we reach the freezing point, and now what happens? Well, we've got both liquid and solid present in this region. And so what happens is, well, it starts off right here as all liquid. And when we're done, it's all solid. So what we're doing in this region is converting liquid into solid. And so that's what you see. So this part and this part right here, those are liquid, and this part is solid. So over time, and as the heat is released, we're converting liquid into solid. Okay, and then once we've got all solid, then the phase changes over again, and now all we're doing is changing the temperature of the solid. Okay, and so that's what happens in the last region. So we've got this region. The first region is just a T change. This region involves a phase change, but no temperature change. This region is a temperature change, but no phase change. This is a phase change, but no temperature change. And then the last one is just a temperature change. Okay, so you can see that when there's a phase change happening, there isn't a temperature change. And when there's a temperature change happening, there isn't a phase change. So those two things are essentially mutually exclusive, and we can break down the entire process of cooling the gas from 130 degrees C to minus 40 degrees C. We can break it up into 5 regions. 3 regions that involve temperature changes when you just have one phase present, and 2 regions where we have a phase change occurring and there are actually 2 phases present. Okay, either gas and liquid or liquid and solid. Okay, so this is the way that substances, this is the way that you can track what's going on over a temperature change of a substance that actually spans phase changes as well. Okay, so that might not be super legible, but it says that temperature is proportional to kinetic energy, is proportional to particle speed. And this is saying that in stages 2 and 4, the particle speed is staying constant. Okay, so that might not be obvious, but it turns out that it's true because the temperature is not changing. Okay, so the next thing that we're going to talk about is phase changes and how they connect to equilibrium. Okay, so what we can say is that if we have a closed system and all of the particles in that system are at a constant temperature, we're going to have the phases actually reaching equilibrium with one another. Okay, so in the previous picture that we showed, you could have a situation where I remove a certain amount of heat from that region where I've got both solid and liquid. Okay, and then if I closed the system and I kept the temperature constant, I would end up getting an equilibrium between liquid and solid, and I could predict how much liquid and how much solid I should have there. Okay. Another way of looking at it is, for example, here. So I've got a picture of a liquid in a flask, and let's say I pull a vacuum on that thing. I hook it up to a vacuum pump, and I suck all of the gas out. Okay, so what's going to happen in that case is when I suck all of the gas out, I've put the system out of equilibrium. Okay, and we know from Le Chatelier's principle that the system is going to do something. It's going to change in some way in order to reestablish equilibrium. Okay, well, I just took some gas out. So that tells me that from Le Chatelier's principle that I should expect that the system is going to try to replace that gas. Okay. And in fact, that's what happens, because what's going to happen over time, it's not going to happen instantly. It'll take a little bit of time. But what will happen is the high energy particles in the liquid are going to come out and they're going to form a gas. And then eventually what's going to happen at some point is once I have enough gas particles, some of those are going to start hitting the liquid surface and some of them are going to go back into the liquid. Okay, so I'm going to end up having I'm going to reach equilibrium when the rate at which particles come out of the liquid and go into the gas is equal to the rate at which particles leave the gas and go back into the liquid. Okay, and so we can see that in a graph like this. Okay, so this is the pressure of the vapor on the y-axis. This is at constant temperature. And what happens is when I pull out all of the gas with, say, a vacuum pump, then the pressure starts down here. Probably not exactly 0, but it's pretty close. Okay, and the pressure goes up pretty fast. Okay, and in this part, the rate of vaporization, that is the rate at which particles come out of the liquid and go into the gas, is larger than the rate at which particles leave the gas and go into the liquid. Okay, this is partly has to do with, in this early region here, there are basically no gas particles. There are very few gas particles, so there really aren't very many to go back into the liquid. But once I build up more gas particles, then I have more that could potentially go back into the liquid. And so what's happening here is the rate of vaporization is, I think, relatively constant, but the rate of condensation is increasing to the point where right here, starting right here and continuing along, then we're at equilibrium. So that's one of the ways that we can actually recognize that we're at equilibrium, that the forward rate and the reverse rate, that is the rate of vaporization and the rate of condensation in this case, are equal. Okay, so we'll talk more about equilibrium and how to identify equilibrium and so forth in chapter 17. So that's something that we still have to look forward to. But for now, we can basically say that one of the criteria for determining that something is at equilibrium is that the forward rate, whether it's a reaction or a phase transformation like we're seeing here, that the forward rate and the reverse rate are equal. Okay, so you see here that equilibrium is established. So you start off with a situation where the rate of vaporization is higher than the rate of condensation. But what then we see is that a bunch of particles from the liquid leave the liquid and enter the gas. Okay, and so that's happening in this region here. But as long as there aren't that many gas particles, there aren't that many gas particles to condense, and so the rate of condensation is relatively low. But as we have more and more particles enter the vapor phase, then we have more and more particles that could actually condense. And so we see that this curve kind of becomes more and more shallow and eventually just reaches horizontal, okay, which indicates that we've hit equilibrium. All right, well, that is, I think, enough for today. We'll continue with this material next time. So I hope you found this useful, and please let me know if you have any questions.